Hello students, my name is Shashank Shekhar. So till now we have seen the classification and all. Now we will see how this classification helps us to study the physical and chemical properties, right? So there are many observable patterns in the physical and chemical properties of elements as we descend in a group. Okay, so there is similarity in the pattern. Okay, for example, within a period, chemical reactivity tend to be high in group 1 elements and lower in the element towards side. So as we move from left to right, the reactivity decreases, and this is the thing, it increases in the group 17 nonmetals. Okay, now likewise within a group of representative element, reactivity increases on moving left to the moving down the group. So if you move down the group, the reactivity increases, whereas in the previous case the reactivity decreases from left to right, but in the case of group, as you move from up to down, the reactivity increases. But why do the properties of elements show this trend, and how can we explain this property, periodicity? To answer this question, we will look at some theories of atomic structure and properties of the atom. Clear? Now, trends in physical properties. So there are numerous physical properties of elements such as melting and boiling point, heats of fusion and vaporization, energy of atomization, which show periodic variation, right? So there are numerous physical properties. Now, however, we shall discuss the periodic trends with respect to atomic and ionic radii, ionization enthalpy, electron gain enthalpy, and electronegativity. So we'll not talk about physical properties much more. We'll talk about this property, means not these physical properties like boiling point and melting point. We will mainly talk about this ionization enthalpy, electron gain enthalpy, and electronegativity. Right? Clear? Okay. Now, first is atomic radii. We can very well imagine that finding the size of atom is a much more complicated thing. We know that because it is very small. So, because size of an atom is very small, it is 1.2 into 10 to the power minus 10. It is around this. Okay. Secondly, since the electron count surrounding the atom does not have a sharp boundary, the determination of atomic size cannot be precise. So then, atoms do not have a sharp boundary. Means one atom is not very distinctive from the other atom. There is a very blur picture over there, right? In other words, there is no practical way by which the size of the individual atom can be measured. However, an estimate of atomic size can be known by knowing the distance between the atom in the combined state. So what it is said here is that you cannot determine the atomic radius by studying a single atom because the boundary is not visible, or it is very blurry because there is not precise. Okay, so for that, what do? We just measure the distance between the nuclei. Okay, so on practical approach to estimate the size of an atom is to measure distance between the atom by a single bond, which are connected by a single bond, and from this the covalent radii of the element can be calculated. So this is possible. For example, the bond distance in chlorine is 198, and half this distance is 99 picometers. So this is taken as the atomic radii of the chlorine. Okay, rather than the individual atom, this is taken as the atomic radii. For metal, we have the metallic radii, which is half the internuclear distance between the metal cores in the metallic crystal. For example, so if you take two adjacent copper atoms, they are 256 meter apart. So the metallic radii of the copper is designed to be 128 picometer. Okay. For simplicity, in this book, we use the term atomic radii to refer to both covalent or metallic radii. So for both of this, what do? We use the term atomic radii. We do not use the term separately covalent and metallic. We use the term atomic radii. Atomic radii can be measured by X-ray or other spectroscopic method, right? So these are the atomic radii across the period. You can see that it is decreasing. From lithium to fluorine, it is decreasing. 152, 111, 88, 77, 74, 66, 64. Similarly, in period 3 also it is decreasing as we move from left to right. Okay. Clear? The atomic radii of these elements, these are the trends. We can explain. How can we explain these trends? Okay. How can we explain this trend? So, what we do, we take the consideration of electrostatic force. Okay, so with the help of that, we try to characterize this trend. The atomic area generally increases across the period from the element, and it is same for the second period also. It is because whenever we do that, whenever we go from left to right, we are adding electron on the outermost shell. Now, on adding the electron, suppose initially the pull was between one proton and one electron. Okay, now we have placed one more electron and one more proton. So now the pull is between two proton and two electron. Okay, so the pull will be more stronger. Okay, the pull will be more stronger, right? So that would result the element to shrink. Okay, and that will result in a smaller atomic radii. Clear? Now, within a family or a vertical column for the periodic table, the atomic radii increases regularly with atomic number as illustrated in the figure B. So for alkali, metal and halogen, as we descend down the group, the principal quantum number increases and the valence electron. So what is being said here is that as we move from up to down, the atomic radii increases. This happens because the inner energy are filled with the electron, which serve to shield the outer electron, right? And consequently, they experience less and less force, and at last, their size increases. Clear? So this is the table that is being set here about a group. So as in from lithium to cesium, the size is increasing, and this is very obvious. Same is the case for fluorine to instantanium, right? Okay. Clear? Note that atomic radii of noble gas are not considered here. Being monoatomic, their value are very large. Okay, so if you just look at the size of the say noble gases, then they're always in the non-bonded state, so their covalent radius cannot be determined, and neither they are found as a neither they are in the form of the metallic form, right? So it is very difficult to do that, and therefore they are having very large size. Okay, being monoatomic, they are having very large size. In fact, radii of noble gas should be compared not with the covalent radii but with the van der Waals radii of the other element. So van der Waals radii is something different from the covalent radii. Now ionic radii, next is ionic radii. So after the removal of an electron, it results in the cation, which is an ion. Okay, right? Now, whereas the gain of electron leads to an anion. Okay, now the ionic radii can be estimated by measuring the distance between the cation and anion in an ionic crystal. So what do? We take a crystal and we measure the distance between the cation and anion, and that is called as the ionic radii. In general, the ionic radii of element exhibit the same trend as the atomic radii. Clear? So we have seen that the trend in the ionic radii is same of the atomic radii. So this thing should be kept in mind that the charge should not change. Okay, we cannot change the charge here. So we are talking about the one which are having the same charge, right? So this should be very clear. Okay, now let us have a general perspective of what a cation and anion size looks like. So if I talk about the cation, so since we have removed one electron from the outermost shell, then now the number of proton has increased, right? Now this proton will exert more force on the outermost shell. Okay, so think it in this way. Initially, we have say 6 electrons, right? And what happens here? They have 6 electrons and 6 protons. Okay, now 6 protons were exerting the force on 6 electrons. Now we have removed one electron. Now those 6 protons are intact, but electrons have reduced. Okay, now each of the electron will experience a greater force, and that is the reason its size will contract. Okay, so we can see that a cation is smaller than a cation is smaller than its parent atom because it has fewer electrons. Okay, what about the size of anion? So how do we form an anion? We form an anion by plugging or by putting one electron inside it. Okay, so when we put one electron inside it, what will happen? First of all, each electron will experience a reduce in the force. Okay, first thing. Second thing, there will be more repulsion between the electrons and electrons because repulsive force is increasing and attractive force is decreasing, right? Now due to this reason, to just lower their energy, what will happen? The size of the atom will increase so that the repulsion can be reduced. Okay, and that results in a greater size of an ion. So this thing should be always in your mind, that a cation will always have a smaller size than the parent atom, and more is the charge on the cation. Okay, more is the charge, positive charge on cation, more will be the contraction in its size. Whereas more the charge on the anion, or more the negative charge on an anion, larger will be the size of that atom due to repulsion. So for example, the ionic radii of fluoride ion is 136 picometer, whereas atomic radii is 64. So you can see what a large difference is being displayed here. So we are just almost doubling it. Okay, 4 to the 8, 6 to the 12. Okay, so we are making it even greater than the double. Where on the other hand, if you talk about cation, so the size of the sodium atom is 186 picometer. Okay, whereas for sodium plus ion, this size reduces to 95, again half. So this is the reason we say that the cation is smaller than the parent atom, whereas anion is greater than the parent atom. Now we will talk about isoelectronic species. Okay, so what is isoelectronic species? First of all, the atoms or ions which contain the same number of electrons are called as isoelectronic. For example, O2 minus, F minus, Na plus, and Mg2 plus. How can we see it? So if you take the case of oxygen, it has how many electrons? It has 8 electrons, right? Now what we have done? We have added 2 negative charge. It means that we have added 2 electrons. So what is the total number of electrons now? 10. Okay. What about fluorine? Fluorine has 9 electrons. We have added 1 negative charge. Okay. So 1 electron will be added. So that will result in again 10 electrons. So see, both have the same number of electrons. What about sodium? So sodium has 11 electrons. Now we have removed 1 electron because there is a positive charge. That would again result in 10 electrons. And Mg2 plus, okay, magnesium 2 plus has 12 electrons. Again, it has a 2 positive charge. It means that we have removed 2 electrons. So there are total of 10 electrons. Means all of these 4 species have same number of valence electrons. That means number of electrons, that is 10. Now, since the number of electrons is same, how you will decide the size? If I ask you how you will decide the size, then your answer should be simple, that by looking at the charge. Okay, so let us see. Their radii would be different because of the different nuclear charge. So this thing is obvious. The cation with a greater positive charge will have a smaller radius. Okay, so which is the greater charge? One with carrying the greater charge, it is Mg2 plus, so it will have the smaller radius because of the greater attraction of the electron to the nucleus. So this thing is obvious. Now the anion with a greater negative charge will have a larger radius. It means that O2 minus will have a larger radius. So this is very important to remember, that how does charge emphasizes, or how this charge puts a check upon the radius, right? In this case, the net repulsion of the electron will outweigh the nuclear charge and the ion will expand in size. Okay, so this is for anion, that the repulsion will just dominate and it will increase the size of the ion. Clear? Okay. Now, next. Which of the following species will have the smallest size? So we have magnesium, magnesium 2 plus, aluminium, aluminium 3 plus. So if you look at if you look at the periodic table, then you will find that potassium, calcium, magnesium. So magnesium falls in the which series? In the fourth series, in the fourth period. Okay, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum. So it falls in the fourth series. Magnesium also falls in the fourth series. What about aluminum? So aluminum is in the third series, right? Clear? Okay. Now we will look upon the charge, right? So atomic radii decreases all across a period. We know that cations are smaller than their parent atoms. It is also obvious. Among isoelectronic species, the one with a larger positive nuclear charge will have a smaller radii. So what is being said here is that, see, they both have the same number of electrons. Okay, so if I talk about all these 4 elements. So first of all, of course, this one is cation. So this will have the smaller charge as compared to these two. And the one with a greater charge will have a smaller radii. Therefore, aluminium 3 plus will have a smallest radii. What about the largest species? So of course, magnesium falls in the next series, that in the fourth series. For that reason, magnesium will have the greater radii. Clear? Next is ionization enthalpy. So what is ionization enthalpy? So ionization enthalpy is basically the measure of tendency to remove an electron, or in more thermodynamic terminology, I would say that it is the amount, or it is the enthalpy change when electron is removed from an isolated gaseous atom. Okay, so when we remove the first electron, it is called as first ionization enthalpy, right? So it represents the energy required to remove an electron from an isolated gaseous atom in its ground state. Okay, so it should be in the gaseous state plus in the ground state. It should not be excited, right? Suppose this is our equation to represent that. See, this is our suppose element we have named as X, which is having a state of gaseous. We have removed one electron, so it has gained one positive charge and one electron has been released. What is the ionization enthalpy? So it is basically the enthalpy change during this reaction. Okay, and it is expressed in terms of kilojoule per mole. Similarly, as this is called as the first ionization enthalpy because we have removed the first electron, we can remove another electron from the same X plus. So that would result in X2 plus, right? So it is the energy that is required to remove the second electron from the X plus, that would result in X2 plus. So this is called as second ionization enthalpy. Okay. Now energy is always required to remove an electron, so it will be always endothermic. Okay, this reaction will be always endothermic. The second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove an electron from the positive charge. So this is the most important point here. So if you ever compare the ionization enthalpy for the similar atom, then the first ionization enthalpy is always less than the second ionization enthalpy. What is the reason behind it? The reason behind it is that because initially when we talk about this first ionization enthalpy, then we are removing one electron from a neutral atom. Okay, this is a neutral atom, so we have to remove one electron. So but when we are removing the second electron, we are removing it from a atom that is already bearing a positive charge, right? So if something is bearing a positive charge, then it is in the need of stabilization. That means it needs electron, and instead of adding electron, you're taking one out of it. So that would require a greater amount of energy. So always for a given species, the second ionization enthalpy will be greater than the first ionization enthalpy. In the same way, so if you just follow this order, now if you talk about the third ionization enthalpy, suppose you have to convert aluminum to aluminum 3+. We have seen aluminum 3+. So we have to remove an electron from already from an atom that is already a bivalent cation. Okay, already a bivalent cation, so it will require even more energy. So the term ionization enthalpy, if it not qualified, is taken for the so this is very important line. So if it is not mentioned that for which ionization enthalpy we are talking about, then it is taken as granted that it is the first ionization enthalpy. Now the periodicity of the graph is quite striking. So in the same way, we will see that the third ionization enthalpy is greater than the second ionization enthalpy. Okay, so until and unless it is not mentioned that which ionization enthalpy is being talked about, you can assume it as first ionization enthalpy. And here is a plot of first ionization enthalpy against atomic number. So as the atomic number is increasing, this is the trend that the ionization enthalpy follows, right? Okay, the periodicity of the graph is quite striking. Okay, why it is, you can see that it exhibits a periodicity, right? It is a periodic graph, of course, right? And at the top of the each graph we have a noble gas. So that thing is mentioned here, so which have closed shell and very stable configuration that have a maxima, whereas the minima occur at the alkali metal. See, lithium, sodium, potassium, rubidium, cesium. So they are the one which are having the minimum first ionization enthalpy. In addition to that, we will notice two trends. The first ionization enthalpy generally increases as we go from left to right and decreases as we descend in a group. So you can see here that first of all it increases as we're moving from left to right in a period, and as we are moving in a group. So suppose this is a group. Okay, this is a group of noble gases. So the one with the highest is helium, then neon, then argon, then krypton, then xenon. Similarly, lithium, sodium, potassium, rubidium, cesium. So as we move down the group, the ionization enthalpy value decreases, whereas across the period, the ionization enthalpy value increases. Right? Now we can say that the atomic radii and your ionization enthalpy are in very good accordance with each other, because as the atomic radii is decreasing, the ionization enthalpy is increasing, and that thing is obvious because we have to apply a greater amount of force to extract an electron because they are now closer to the nucleus. Okay, now the attraction of the nucleus towards the nucleus, the attraction of the electrons towards the nucleus and the repulsion of the electrons from each other. So sometimes we will see an anomaly because this thing is not only about that attraction from the nucleus. This thing is about the half-filled orbital and full-filled orbital stability. This thing is about the repulsion. So all these things are just clinging upon one another, and that results in a very abnormal first ionization enthalpy when you go into the D block elements. Okay, so when you move from main group to D block element, because there are the number of electrons increases, so the number of interaction increases, plus the screening or the shielding effects comes into play, and therefore that would result in a very abrupt ionization enthalpy that wouldn't be explained easily. Clear? Okay. Now, for example, the 2s electron in lithium is shielded from the, so if I talk about the shielding effect, the 2s electron in lithium is shielded from the nucleus by the inner 1s electron. As a result, the valence electron experience a net positive charge which is less than the positive 3. So it should of course experience plus 3 charge, but since this is being shielded, so if you think of it in this way, so suppose you're standing, right? You're standing in front of a wave, okay, sea wave, right? And in front, between you and sea wave, there is a wall. Clear? Whose height is, suppose, half the height of the sea tide that you can experience, right? So what will happen? So whenever that sea tide will come, you will experience the force of the sea tide decrease because that wall is shielding you from it. Okay, so this is in this way you can understand this thing, that it is being shielded by the inner core electron. Clear? And the shielding is effective when the orbital in the inner shells are completely filled, because without electrons there is no existence of orbital, and if there is greater density of electrons that are present in the inner core, they will experience more shielding. Clear? Okay. Now this situation occur in cases of alkali metal which have single outermost ns electron by a noble gas electronic configuration, because inside this, so if we talk about the alkali metal, so that alkali metal has one electron in the outermost shell, and inside it there is a completely filled shell. Okay, that would result in a very high shielding effect. So that decreases the influence of the proton on the electron, and it can be removed easily. So it has a lower ionization enthalpy. So when we move from lithium to fluorine across a period, the successive electrons are added to the orbital in the same principal quantum number, and the shielding by inner core electron does not decrease very much to compensate for the increased electron of the charge. So what is being said here is that, so we have said that, okay, there is a repulsion from the inner core electron or the shielding from the inner core electron. Then why do we see an increase in or decrease in the size when we go from left to right? Why there the electrons are experiencing more forces? Because the shielding effect is same, because the inner core electron number is not changing, but the outer number of electrons is changing. So a net effect would result in a greater attraction. Thus, across a period, increase in nuclear charge outweighs the shielding. Clear? Consequently, the outermost electron are held more and more tightly, and the ionization enthalpy increases across a period. Clear? Now, as we go down the group, we have already discussed it. So as we move down the group, the number of shells increases, so the size of the atom increases. Therefore, the electrons are at a greater distance from the proton, and we can just simply explain it with the help of, say, electrostatic force of attraction. If the distance between the charges is increasing, the force of attraction will decrease. In this case, increase in shielding outweighs the increasing nuclear charge, and the removal of the outermost electron requires less energy around a group. So what is being said here? So when we move down a group, two things. So first, the distance is increasing. Second, most prominent thing is the shielding is increasing. Okay, this outermost electron gets more shielded away from the proton as compared to the period in which the number of shielding electrons were not changing, but in this case the number of shielding electrons are changing, and it is of course increasing, so that electron can be removed easily as compared to the one which is having a lower atomic number in the similar group. So we will also notice that the first ionization enthalpy of boron is Z is equals to 5 is slightly less than that of beryllium, even though the former has a greater nuclear charge. So we can say that S electron is attracted to the nucleus more than a P electron. So this is the reason. So if I am removing an S electron, then it will require more energy because it is more penetrated toward the nucleus due to its uniform size, as compared to the P orbital, which is kind of not uniform in nature. So uniform means S orbital is spherical in shape. So that means each electron with the electron density is being equally pulled by the proton. But as we take in account for the p orbital, some of the electrons are far away, some of the electrons are closer to that. So that results in an uneven distribution or more diffuse shape, and hence less force of attraction. Now when we consider the same principal quantum number, S electron is attracted to the nucleus more. So this thing we have done. In beryllium, the electron removed during the ionization is S electron, whereas the boron, in case of boron, it is removed for p electron. So that is the reason the beryllium requires more force. Okay. Next is ionization enthalpy. So the penetration of 2s electron to the nucleus is more than that of 2p electron, and hence the 2p electron of boron is shielded from the nucleus by inner core electron than the 2s electron of the beryllium. So what is being said here is that first of all, the 2p orbital is more diffused in shape, and second thing is that the 2s electrons that comes before the 2p electron, they shield the 2p electrons more efficiently because of its uniform shape. Okay, then that is the reason they have a lower ionization enthalpy. Thus, it is easier to remove the electron from the 2p orbital. Another anomaly is the smaller first ionization enthalpy of oxygen compared to nitrogen. So oxygen has a greater ionization enthalpy, smaller ionization enthalpy than the nitrogen, although its size is what? So if it has a smaller ionization enthalpy, it means it should have a greater size, but instead oxygen has a smaller size, but although it has a smaller ionization enthalpy, and the reason is the stability of the half-filled orbitals. In case of nitrogen, we have a half-filled orbital or maximum exchange energy, due to which it is difficult to remove an electron from the nitrogen, where in case of oxygen, as you remove an electron from the oxygen, that would result in symmetrically filled orbital subshell, and hence stability is increased. Next is electron gain enthalpy. Okay, next is electron gain enthalpy. So what is electron gain enthalpy? It is basically the energy that is released or absorbed, depending upon the element that we're talking about, when a electron is added to a neutral gaseous atom, and it is represented by delta electron gain H. Okay, so here is the equation for you. We have an element in the gaseous phase, we are adding an electron to it, and we are getting X minus, because one electron is added, therefore it results in a negative charge, and this reaction must involve some enthalpy change, and that enthalpy change is called electron gain enthalpy. Now, depending upon the element, the process of addition of electron can be endothermic or exothermic. So this is very, very important. So in case of ionization enthalpy, it is always positive because we have to apply some force to take it out. But in case of addition of electron, it may be endothermic or it may be exothermic, depending upon the element that we are talking about. For example, the halogens have very negative electron gain enthalpy, means high amount of energy is released because of the gain of noble gas configuration. Clear? Okay, but if you talk about the noble gases, then they have a very they have a very positive electron gain enthalpy because we have to destabilize this octet. Now, on the other hand, noble gas have large positive electron gain enthalpies because the electron has to enter. The same thing is written. So they have a large positive, whereas the halogen have a large negative value. So this is the thing that I want to focus on, that electron gain enthalpy is not something which is uniform. It can be positive or it can be negative. Clear? Now it may be noted that electron gain enthalpy have larger negative value toward the upper right of the periodic table preceding to the noble gas. So as we move from left to right, then the electron gain enthalpy value decreases because Upon addition of electron, it becomes closer to the noble gas configuration. Okay, so what about the variation in electron gain enthalpy? So as compared to electron ionization enthalpy, it is less systematic. Okay, because electron gain enthalpy become more negative with increase in atomic number across a period. The effective nuclear charge increases from left to right across a period. So I would expect that the incoming electron will experience a greater force of attraction from the inner proton due to the decrease in signs, and hence the electron gain enthalpy would be closer to the positively charged nucleus. So that is the reason that we should expect more positive electron gain enthalpy, okay, or less negative electron gain enthalpy. However, an electron gain enthalpy of oxygen or fluorine is negative than that of succeeding element, okay, because it is highly electronegative in nature. So we'll talk about electronegativity also, and due to the fact that they will gain a stable electronic configuration. So to talk about when an electron is added to oxygen or fluorine, the added electron goes to the smaller n is equals to 2 quantum number and suffers significant repulsion from other electrons present in this label. Okay, so that is the reason its value is less negative because of their smaller size. Now here are some values of electron gain enthalpy that is being given. So you can see that as we move from up to down in the alkali metal, then what happens? The electron gain enthalpy value become less and less negative. Okay, whereas if you see in this case, then the noble gas have positive values. Okay, oxygen has negative values. Oxygen group or chalcogen group has negative values, and its negative value increases or decreases. So see, it is not systematic. So that is the reason we are saying that electron gain enthalpy is not systematic, and similar is the case for group 17. Right? Clear?